So at a workshop on astrophysical evidence, one question we might ask is there anything epistemically distinctive about astrophysical evidence in contrast with other sorts of scientific evidence? For example, does the subject matter of astrophysical research give rise to certain special evidentiary challenges or opportunities? Is the nature of astrophysical evidence notably distinct from that of astronomy or of cosmology, or from laboratory-based experiments, such as laboratory-based experimental physics? So in the philosophical work that's been done on this issue of astrophysical evidence so far, which is a pretty slim amount, I notice, and maybe you have too if you've looked into this at all, that a particular contrast is often employed in framing what is distinctive about astrophysics and astrophysical evidence. So this contrast, this is the contrast between evidence gathered via observation of a worldly target or target system, and then evidence gathered by intervention on a worldly target or target system. So usually because astrophysics is paradigmatically concerned with objects and systems at astounding physical remove from researchers, astrophysical evidence is situated on the observation side of this contrast between observation and intervention, and certainly not on the intervention side. However, I think it's an unnatural and in many cases misleading or even outright false move to cast the evidence gathering activities of astrophysicists as observation, although I think it happens all the time. And there are also prominent instances of astrophysical research in which evidence is gathered via intervention, on laboratory systems, no less. So today, I will actually not argue that astrophysical evidence belongs on the intervention side of the contrast as opposed to the observation side. Rather, I'm going to argue that observation and intervention are irrelevant to the empirical nature of astrophysical evidence, and hence for its epistemic utility in learning about astrophysical objects, systems, and their processes. So what matters instead of whether the evidence in question is gathered by observation or intervention is that the evidence derives from a causal chain that has one end anchored in the worldly target of interest, and that this is what matters is, I think, actually quite a general feature of empirical evidence and not of astrophysical evidence in particular. So perhaps my talk today will have the effect of making astrophysical evidence look less exceptional than it otherwise might, but I don't think anyone in this room will love it any less as a result. So proceed anyway. So I'm going to start fleshing out these remarks a bit more by considering three probably familiar theses that rely on the contrast between observation and intervention, which I reject. And then I'll explain how and why I think we ought to sidestep the whole observation-intervention issue. And finally, I'll turn to two cases on which to test this alternative approach to thinking about astrophysical evidence. And I'll warn you in advance that I don't, I'm still really learning about these two cases. And while I can't offer you a tidy story today, I believe that thinking about them in the manner I'm going to describe has led to some interesting questions for further investigation. So hopefully that will lead right into our discussion. So one familiar thesis is that astrophysics, along with astronomy and cosmology, is a distinctly observational science, since its targets are too distant to experiment on, right? And there are two main reasons that I reject this thesis. One is the general point, that much contemporary science, including astrophysical research, is conducted with sophisticated instrumentation and detectors, while the word observational, both linguistically and historically, still connotes perception with the human senses, specifically sight. And I think this bothers physicists less than it bothers philosophers, but I think it's still worth saying. The second is that observational science here is contrasted with experimental science, that is, with intervention. It relies on the idea that a distinctively observational science is precisely one that fails to be experimental, one in which intervention on the target system is impossible or otherwise absent from that practice. And as an example of someone stating this thesis in print, I'll pick on Sabile, who writes in her Philosophy of Astrophysics piece, I mean, one of the very few Philosophy of Astrophysics pieces that there are, besides Mauricio's, She writes, astrophysics and cosmology share a common problem in that they both need to acquire knowledge of their objects of research without directly interacting, manipulating, or constraining them. And she's, of course, not the only one who says this sort of thing, but she's just an example. But I think construing astrophysics in this way sits uncomfortably with research like the quote-unquote laboratory astrophysics advertised by the Harvard-Smithsonian Center for Astrophysics, or laboratory-based dark matter experiments, such as ones that Cisco alluded to and that my friends at University of Washington are doing with ADMX, laboratory-based nuclear astrophysics, laboratory-based investigations of Hawking radiation, and an example that I'll turn to later, laboratory-based investigation of hydrodynamical instabilities of the sort thought to occur in supernovae. So how should we make sense of these astrophysical experiments, these examples of laboratory-based astrophysical research? If astrophysics is distinctly observational, like astronomy, then it would be wrong to count these experiments as part of astrophysical research. However, I think, and I hope you'll agree, that it would be better to see if we can make sense of these experiments as properly belonging to astrophysics in keeping with the manner in which the researchers themselves are construing their own work, even at the expense of rejecting Thesis 1. So the second thesis that I want to reject is significantly more controversial, I think. It's as follows. Astrophysics, along again with astronomy and cosmology, invites the use of simulated data in the place of experimental data, since its targets are too distant to experiment on. An example of someone who holds this view is philosopher of science Margaret Morrison. Here's a quote. "There are a variety of contexts where computer simulations do take center stage as the source of experimental knowledge simply because the systems we are interested in are inaccessible to us. An example is the evolution of spiral structure in galaxies. Because the typical time and distance scales are so vast, the only way experiments can be performed is by simulating the system on a computer and experimenting on the simulation. In the astrophysics case, we may want to say that simulation is an acceptable source of experimental knowledge simply because we are unable to conduct materially based experiments in the way we can with other types of systems." And here she says, we may want to say that the simulation, she actually goes on in the next sentence to say that, in cases where, we could conduct both experiments and simulations, we might still prefer to, so she actually means something quite strong here, I think. She thinks that we can, in some cases, substitute in synthetic results for where we would otherwise want experimental or what I would call empirical results. So Morrison's thought here seems to be that insofar as we can't experiment on astrophysical objects or systems, but we can, in a sense, experiment on model astrophysical systems by running simulations, then we can substitute simulated data where empirical data would have been used to generate astrophysical evidence. But this logic, as I said, just seems wrong to me. It sounds like, given that you don't have the thing that you really want, substitute something different for that and use it instead. But surely whether or not the proposed substitute is apt for the purpose matters to the prudence of this strategy. And I think simulated data lacks the relevant feature of data generated by experiment in this context, namely having been produced by interaction with the worldly astrophysical target. So the third thesis I want to reject is the most controversial of the three, but it's kind of fun, so I wanted to show it to you. Astrophysics, along with astronomy and cosmology, is not properly scientific at all, since intervention is characteristic of properly scientific methodology, and the targets in astrophysics are too distant to experiment on. So someone does, in fact, hold this view, or at least held this view. I think this thesis is expressed in philosopher of science Ian Hacking's super fun 1989 article called Extragalactic Reality, the Case of Gravitational Lensing. And if you haven't read this already, you absolutely need to read it. It's super fun. this is the article where he says, quote, galactic experimentation is science fiction, while extragalactic experimentation is just a bad joke, right? He also says the method of astrophysics is the same as that of astronomy in Hellenistic times, model, observe, and remodel in such a way as to save the phenomena. And natural experimental science is a matter not of saving phenomena, but of creating phenomena. But in astrophysics, we cannot create phenomena, we can only save them. He pretty much goes off on a rant in this article about how astrophysics is stuck in old methods, that legitimate natural science essentially left in the dust in the 17th century. And I'm actually going to read you a longer quote from this article, mostly because I think it's so fun, but also to demonstrate that at least, as I said, one person once held this striking view expressed in Thesis 3. So Hacking writes, I don't imagine that science aims at anything at all. But if we do use this metaphor, then it seems to me that most natural science aims more at manipulating and interfering with the world in order to understand it. Hence, saving the phenomena seems an entirely subsidiary aspect of scientific activity. There is one, and perhaps only one, branch of science where the tag to save the phenomena has a central place: astronomy and astrophysics. Surprise, surprise. Is it an accident that the catchphrase has a place in the family of disciplines for which it was coined and nowhere else? No. The technology of astronomy and astrophysics has changed radically since ancient times, but its method remains exactly the same. Observe the heavenly bodies, construct models of the macrocosms, try to bring the observations and models into line. In contrast, the methods of the natural sciences have undergone profound transformation, chiefly in the 17th century. Or one might say, the natural sciences came into being then and thereafter, while astronomy is not a natural science at all. The organization of many university faculties and departments reflects this. The transition to natural sciences was precisely the transition to the experimental method, to interference in nature, to the creation of new phenomena, right? Okay, so fun, right? But fun, but I think this view of natural science is too restrictive. Experiment, interference, and creation, the manipulation of nature, are not necessary for properly scientific research. Here, Hacking draws the line in the wrong place, and perhaps here he is being intentionally hyperbolic, since elsewhere he couches the connection between intervention and the properly scientific more gently. But at any rate, I think the right question is not whether there is a properly scientific astrophysical, whether or not, I don't think the right question is whether there's properly scientific astrophysical evidence at all, right? So my take is that at least part of what's gone wrong with these three theses is that they all rely on the contrast between observation and intervention. Astrophysical evidence is not, strictly speaking, observational, but some of it involves intervention after all. And regardless, what matters for the epistemic utility of astrophysical evidence is not that such evidence is derived from observation, that it fails to derive from intervention, or vice versa. Observation and intervention are irrelevant to the empirical nature of astrophysical evidence. What matters is that the evidence derived from a causal chain that has one end anchored in the worldly target of interest. So, in other words, data, including astrophysical data, are, I would say, empirical with respect to some target when there's an interpretation of the provenance of those data using the resources of some epistemic context, such that the data are products of causal interaction with that target. And an epistemic context, in the sense I intend here, is just a collection of the conceptual, theoretical, and representational resources from the perspective of which data is to be interpreted. So it's important to note that data are empirical relative to a target. Without specifying a target, it's impossible to say whether some particular data are empirical or not. Data are also empirical relative to an epistemic context, and the epistemic context supplies the resources with which the data are interpreted. So, data never speaks for itself, but rather always requires interpretive resources, and in particular, background theory, to furnish a causal story connecting the worldly target of interest to the data collection and recording process. So an important feature of this view of empirical data that I'm defending is the causal production of data. And as I said, to be properly empirical, data should have been produced by causal processes that connect the worldly target of research to the process of data collection and recording from the perspective of the epistemic context in which data are to be interpreted. There is no perspective outside of an epistemic context from which the causal processes can be identified and traced. Indeed, there's no perspective outside of an epistemic context from which a worldly target can be identified in the first place. Yet, using the resources of an epistemic context, it can be possible to answer the question, where were these data produced? Were these data produced by causal interaction with the target? The view of what makes data empirical obviously relies on the notion of causal interaction, which at least for philosophers, is a, I would say, fiercely fraught notion, maybe? Is that true? Still, maybe? At least historically, fraught notion. And I'm not committed to a special theory of causal interaction, and in fact, I believe probably the view to take, is that causal interaction is best understood, from within the perspective of some physical theory, and we should, leave it up to the epistemic context to actually tell us what causal interaction means in the first place. So I'm going to kind of bracket that for the time being. But I think this view is probably compatible with with a variety of ways of spelling out exactly what we mean by causal interaction. So why is it important for the empirical character of data to be connected by causal processes to worldly targets? One important reason in support of this approach is that if one does not require causal production of the data, one risks collapsing the distinction between empirical and virtual data, or synthetic data. I think we should like to be able to say that the outputs of a simulation of X are of X without having been causally produced by X. The products of models and simulations can stand in relations to worldly targets, for instance, representation relations, without having been produced by those targets. To see why causal production matters for the purposes of empirical data and empirical evidence, let's consider a characterization of what makes data empirical that eschews causal production and relies instead on ostension. And I'll briefly argue that this view suffers from a serious drawback. It's not easy to see how it could be applied to data sourced from faraway worldly targets that no one can point to in an act of ostension. So the characterization I want to consider comes from an insightful and philosophically valuable paper by Matthias Kaiser from 1991 titled "From Rocks to Graphs, the Shaping of Phenomena." In this paper, Kaiser develops an abstract characterization of the epistemological structure that carries scientific reasoning from what he calls observable reality, parentheses data, to empirical phenomena. And the basic elements of an instance of this structure for Kaiser are an anchor point and inference tickets. And roughly, the anchor point is the bit of the world that sourced the data, and the inference tickets transform the data by redescription and other operations licensed by theoretical resources, either via bootstrapping or incorporation of accepted background theory, which might include incorporating data collected in other contexts. And although Kaiser goes on to formalize these intuitions, the anchor point becomes O structure and so on, or zero structure. I don't know if it's O or zero, actually. The gist of the idea is as follows. The structure consists of, consists of objects of scientific inquiry together with the simple act of presentation. He says, my basic intuition here is that scientific data rest on raw material that can be presented or reproduced upon request. It's essential, he says, that this level is kept as simple as possible, like this rock here, or these spots on the screen, or in social sciences, these filled-in questionnaires. The structure contains all those things that are to be subjected to scientific scrutiny, i.e. that are to be measured, weighed, radiated, diluted, accelerated, and so on. So on Kaiser's view, what makes data empirical are these original and reproducible acts of ostension, like this rock here. And as I said before, I think that Kaiser's view is ill-suited for faraway targets in virtue of this feature of his account, right? On this account, when the material specimen isn't a rock, isn't present at hand, the scientist cannot anchor the data to it via acts of ostension, like this rock here. And instead, she's forced to anchor her data, not to the worldly target of interest, but to some intermediary, as in these spots on the screen. So let's consider an example of this sort. Like I've got a visualization here from Arecibo displaying spots, right, that can be interpreted as radio signals from distant galaxies. And I apologize, this is sort of more of an astronomy example than an astrophysics example, I guess. But insert your favorite visualized data here. On Kaiser's account, what makes the data visualized here empirical is that they can be picked out by ostension, by some scientist gesturing to the image, these spots on the screen here. This approach locates the empirical at the site where some bit of the world is present to perception of the human inquirer. And in this case, the spots in the image are what is present to the inquirer. But I think, this approach just like misses the point. The data displayed here are empirical with respect to galaxies. They are, data encoding the radio frequency emissions of galaxies over time in virtue of being produced by the interaction of the electromagnetic radiation emitted by those galaxies traveling through space and interacting with the receiver of, at Arecibo, and subsequently the rest of the readout apparatus of the telescope. Right? Okay. So far I've suggested that casting astrophysical evidence as characteristically observational as opposed to as generated by intervention on a target system is less helpful than approaching astrophysical evidence with the following two questions. What is the worldly target that the research seeks to investigate? And what is the data the result of causal interaction with? If the data has been produced by causal interaction that we can trace from the worldly target using theoretical resources of our relevant epistemic context, then I think we can call this data empirical. It could still be poor data, but I think we would call it empirical. However, if construed from the perspective of an epistemic context in which researchers are working, the production of data is not derived from causal interaction anchored in the worldly target, then the data cannot be empirical with respect to that target. Empirical data, may have been produced via observation or more generically by detection or intervention, but not, for instance, by modeling or computation alone. So with this approach in mind, I'd like to turn to two cases in order to show how this approach can generate at least some questions. So let's consider a specific example of laboratory-bound astrophysical experiment. So the National Ignition Facility at Lawrence Livermore National Laboratory uses a 4 megajoule laser facility to study matter in high energy, high density states, including, among other things, nucleosynthesis in stars and supernovae, instabilities in supernovae, opacity of stars, black hole accretion, nuclear reactions in stars, planetary interiors, in short, astrophysics. The data gathered from the National Ignition Facility experiments is clearly empirical with respect to some target. It's not, for instance, the result of a computer simulation. But is it really astrophysical empirical data? After all, these experiments at NIF are not performed by intervening on stars themselves. So we could ask, are the scientists just wrong to call such activities astrophysical experiments? Is this just a bad joke, right? For present purposes, I just want to focus on a particular paper from 2018. In this paper, the authors report results from a series of National Ignition Facility experiments first designed in 2009 that aimed to study the Rayleigh-Taylor hydrodynamical instability, which occurs at the boundary between fluids of different densities, where somehow the lower density fluid is being pushed into the higher density one. And it's thought to occur in supernovae at the interface between the forward shock moving outwards into the relatively low density circumstellar media around the star and the induced reverse shock in the relatively high density expanding stellar ejecta. So the researchers wanted to investigate the possible effects of high energy fluxes on the structure of RT instabilities in supernovae. And as the authors explain, since, quote, the temperature is much higher in the shocked, less dense circumstellar media than in the denser ejecta, this leads to the possibility of radiative or conductive transport of energy into the denser ejecta, which can in turn affect the evolution of the RT instability by removing material from the interface between the two shocks where the instability is evolving. So they're studying a particular type of instability in these supernovae, and they're interested in what happens to these, the structure of these instabilities when there are high energy fluxes present as well. So this massive laser system is focused on a tiny little hologram held in place at the tip of this spike. And the lasers radiating the hologram produce X-rays, which then are absorbed by the darker colored represented package on top of that cavity. And this produces a blast wave through relatively high density plastic into lower density foam. And the experimenters report on two different conditions, a high flux case depicted in the top right radiograph, which is an image of the physical experiment, and a low flux case, which is the bottom radiograph. So notice in the high flux case that there are no mushroom caps on the RT spikes. They just kind of look like blunt fingers. And that the height of the region of mixed density is smaller than in the low flux case. So model parameters fitted to empirical data from supernova 1993J suggest that the energy flux from heat conducted from the shocked circumstellar medium back into the shocked stellar ejecta are evidently larger with respect to the physical system than those present in the National Ignition Facility experiment. Right? So you're trying to set up this sort of like analog laboratory experiment to the astrophysical case. Modeling a particular supernova suggests that the energy fluxes in the supernova are larger, taking into account the nature of the two cases than than the analog cases in the laboratory experiment. So insofar as the structure of the RT instability was affected, we have blunt fingers instead of mushroom-capped ones, and they're shorter than they should be. In the experimental setup, the structure in the case of the supernova should have been affected too, because the fluxes were even greater. The analogous fluxes were even greater. So the researchers conclude, quote, realistic models of supernova remnants must account for the effects of thermal conduction to accurately predict the evolution at epochs immediately following the shock breakout. And the question I want to pose at this point is, how should we construe the evidence generated by the National Ignition Facility experiment? Is this astrophysical evidence? Or physical evidence from which one might make astrophysical inferences? How is it exactly that the conclusions about supernova remnants are supposed to have been drawn from the terrestrial experiments? The short answer, but I think an answer that's not quite satisfactory, as you'll see, is that one can argue that the physics, the RT instabilities under the influence of high energy fluxes, is the same in both cases, such that in experimenting on X-ray blasted plastic and foam, researchers are probing the very same kind of physics played out in far distant supernovae. So indeed, the authors appeal, in this paper that I looked at in 2018, to an earlier paper, this one by Rutov et al., that lays out particular criteria for establishing the physical similarity between laboratory conditions and those occurring in, naturally in supernova hydrodynamics. And here are those criteria. And for present purposes, I just want you to notice that a key assumption of these criteria for establishing the similarity between the two physical systems is zero thermal conductivity. And so according to this paper, if those similarity conditions are satisfied in an experimental and a natural system, then the two systems are identical with respect to their hydrodynamical physics. The similarity can break down, however, when the energy flow by particle heat conduction and or energy flow by radiation flux are non-negligible. So again, how should we construe the evidence generated by the National Ignition Facility experiments? Is this astrophysical evidence? The evidence produced at Lawrence Livermore is neither the result of observations of supernovae, nor the result of interventions on supernovae, but these issues are irrelevant to the epistemic utility of the evidence in this case. Instead, we should ask, I think, what is the worldly target of the National Ignition Facility research? And by causal interaction with what has the evidence been produced from the perspective of the relevant epistemic context? So perhaps we should say that the worldly target is the supernova, the SN 1993J, yet that the causal interaction producing the experimental data is with the NIF plastic and foam targets, thereby ruining the empirical nature of the data with respect to astrophysical targets. Or perhaps we should say that the NIF plastic and foam targets are the worldly targets of research too, but that would ruin the astrophysical nature of the data. But to recover a sense in which this experiment produces astrophysical evidence, we would do better, I think, to construe the worldly target as the general class of hydrodynamical instabilities in high energy, high density states of matter. Then insofar as laboratory systems and far removed astrophysical ones instantiate this very same physics, investigating the nature of high energy fluxes on hydrodynamical instabilities in laboratory plastic and foam is just to investigate the identical physics playing out in astrophysical contexts. NIF data are empirical with respect to high energy density states of matter and their behavior, since there is an interpretation of the provenance of those data such that they are the products of the causal interaction of the matter energized and confined by the NIF lasers with the laboratory detector systems. Insofar as such high energy density states are instantiated in faraway astrophysical systems also, the data gathered in the NIF experiments can be used to constrain astrophysical theorizing. But perhaps at this point you still have a lingering worry that I share. If the argument from hydrodynamical similarity requires that the energy flow from the heat conduction in the systems is negligible, but the experiment in question is designed to investigate how high energy flux from heat conduction influences the structure and evolution of the hydrodynamic instability, does the very aim of the experiment undercut the specific conditions to the astrophysical targets, like SN 1993J? So regardless of the answer to this question, it's something I just need to probably, like the physicists are probably right. I probably just haven't read it carefully enough. I probably just got to spend more time with this case. But regardless of the answer to that question, I want to submit that attending to the worldly target and the causal production of the data better helps us at least appreciate what the interesting features and difficulties of this research are, and to avoid getting distracted by issues about observation and intervention. If anyone knows the answer to this question, I would be happy to hear it. Okay, so the second case I want to consider today, even more briefly, is the recent results from the Event Horizon Telescope. And we've already seen this beautiful image today. I bet you know already that these results come from data taken from M87 star, amalgamated from 8 stations, including one here in Spain, together composing a very long baseline interferometer that is processed using a suite of presuppositions, including the distance to M87, a geometrical Earth model to precisely locate the stations with respect to one another, a clock model to synchronize the data across the stations, which is really important, as well as, for instance, models of the atmospheric conditions and thereby corrections to the data. So the various base pairs of this long baseline interferometer system sparsely sample the radio sky in Fourier space. And from this patchy data, an image in real space has to be reconstructed. So I'm just going to pull some plots from the published papers. This isn't like a deep case where I've like done a lot of background work, going behind the publications. I'm just going to like pull some plots from the published pieces and raise a couple questions. So okay, you got to get from this sparse data in Fourier space to the real image. You have to reconstruct the image. What the publications tell us is that early efforts by 4 subteams to reconstruct an image of the black hole accretion disk from engineering data yielded these 4 different images. And so I think, to the eye, they look pretty varied, right? Like one of them is almost a complete ring. This one's like kind of lopsided over here. And the variation stems from different assumptions made by in the reconstruction process by these different subteams. So to determine how best to reconstruct the image from the science data, the teams tested various imaging pipelines on synthetic data, for which the corresponding ground truth image was already known. The team then developed 3 different imaging pipelines and selected top sets of parameters for each of these pipelines based on their performance in reconstructing the synthetic images. So you kind of optimize these 3 different pipelines based on a collection of images that you know really well because you've created them. And these 3 pipelines were then applied to the science data. And, quote, because the angular resolution of the reconstructed images vary among the pipelines, we blurred each image with a circular Gaussian to a common conservative angular resolution, and then averaged together the blurred images from the 3 pipelines to produce the final image of M87 star's accretion disk that we saw in all the newspapers. So, to test whether this reconstructed image is consistent with the expectations assuming general relativity, the image, to bring this image to bear on the theory side, the image was compared with a library of synthetic images, thousands of images generated from a library of simulations generated from different general relativistic magnetohydrodynamic models of black holes. Each model characterized by spin angular momentum and the mass of the black hole and the net magnetic flux over its event horizon. So, excuse me, using these synthetic images generated from these general relativistic magnetohydrodynamic models, the team found that the image of M87 star's accretion disk, quote, is consistent with the hypothesis that is produced by a magnetized accretion flow orbiting within a few RG of the event horizon of a Kerr black hole. Parameter values for M87 star were then inferred using a variety of methods. And I want to note in particular that the inferred mass of the physical black hole is arrived at by a combination of methods, including invoking the general relativistic magnetohydrodynamic models. So these aren't just like, read off that image. So in keeping with the present approach, I don't think this research is well described as an observation of a black hole, although I think that does generate fun news headlines about seeing the unseeable. Perhaps detection consistent with a black hole accretion disk would be better. Less nice news headline, but it's also clearly not an instance of intervention on a black hole. Nevertheless, we can ask, does this research yield empirical evidence regarding black holes? I think the answer is yes. We can say that the worldly target of the research is the M87 accretion disk, and that the data collected via the telescopes here on Earth is empirical in virtue of being produced by causal interaction with it, the accretion disk. The telescope data is empirical with respect to the accretion disk. However, I don't want to, I do want to admit here a kind of uneasiness about a lingering uneasiness about the empirical nature of some of the more heavily processed Event Horizon Telescope results, such as the inferred mass of M87 star, or even the reconstructed images of the accretion disk. So I think that there is empirical data here. There are empirical results here, but a lingering question I have is this kind of image properly construed as an empirical result, or like even going further down the processing line, is something like the inferred mass properly construed as an empirical result? In general, I think to get an empirical result that can actually be used to constrain theorizing, data often have to be heavily processed and transformed. So in this particular case, in order to check the consistency of the data with general relativity via these general relativistic magnetohydrodynamical models of black holes, the data are transformed, but they're also supplemented, right, by assumptions that help to fill in the details that make a reconstruction of the full image from the sky coverage and Fourier space possible. And this is what I'm trying to show you, that those 4 possible pipelines and the 3 that were eventually used in analysis, and the fact that they were, in the end, averaged. This sort of supplementing is not, of course, limited to the Event Horizon Telescope images, nor astrophysics. We can find similar examples in particle physics and certainly climate science. And we might want to say that these reconstructed images are empirical insofar as they are a downstream product of empirical data. But I'm worried that this is a slippery slope, right? Like, maybe empirical data can't be supplemented in any which way and remain properly empirical, right? Like, if you had an almost entirely synthetic image, like simulation that you ran, and a teeny tiny patch of it was generated from empirical data, would we want to call that empirical? Specifically for the purposes of testing the empirical adequacy of our theories. I think another option would be to count any result as empirical insofar as it was generated from empirical data, like the slippery slope case included, but to insist that the manner in which the empirical data influences that result, maybe the supplemented result, the partially synthetic result, to insist that the empirical part makes a difference for distinguishing between the theory, model, or hypothesis to be constrained and its competing alternatives. I think this could be a way to go. However, I'm not yet convinced that this is actually a good way of understanding what's going on in the case of the Event Horizon Telescope images. The collaboration does say exotic alternatives to black holes, such as naked singularities, boson stars, and gravastars, are admissible solutions to GR and provide concrete, albeit contrived models. Some such exotic compact objects can already be shown to be incompatible with our observations, given our maximum mass prior. For example, the shadows of naked singularities associated with Kerr spacetimes with a star greater than 1 are substantially smaller and very asymmetric compared to those of a Kerr black hole. Also, some commonly used types of wormholes predict much smaller shadows than we have measured. So, there's a sense in which within GR they've maybe ruled out some competing alternatives. But again, I think that this is something that maybe we could talk about more. Maybe you have thoughts on. So, that said, I do think that it's crucially important to keep the empirical status of evidence in focus. After all, purely synthetic results could not help us to learn about nature in the same way that empirical ones do, even if those synthetic results could distinguish between competing theoretical alternatives. Right? The empirical part is necessary. So to conclude, I've argued that empirical astrophysical evidence must derive from a causal chain that has one end anchored in the worldly target of interest, but that observation and intervention are irrelevant to the empirical nature of that evidence, and that construing this issue in this way allows us to at least ask, hopefully, more nuanced questions about astrophysical practice and epistemology than we would have in the framing that sets up the question in terms of observation and intervention.
Great. Thank you so much. All right. so let's use 10 minutes or so to address questions directly to Nora's talk, and then we'll move on to kind of more general discussion of the whole day. So questions for Nora? Jacob? Of course.
Oh, no problem. Sorry. Sorry, maybe I should have grabbed it myself. Yeah, I'm sorry. Sorry. Okay. Thank you very much. I think it's this is very fascinating, and there was one point I was already thinking whether the distinction between observation and intervention could already be thought to be kind of well, ill-defined perhaps, or not necessary, is whether, and I'm not sure, I just wanted to ask you whether you think this is the case, whether you can actually understand perhaps even simulation as an intervention, as both an observation and an intervention, or something which actually already shows that this distinction is not something which is very valuable. Yeah, let's leave it at that.
Yeah, I mean, there's a cool literature in philosophy of science on simulation and how it's different from experiment, or how it's the same as experiment, and there's several cool papers on this, like Margaret Morrison is certainly part of that literature. Sherry Rausch wrote a paper that's antagonistic to Morrison's view. There's cool stuff from Wendy Parker and Eric Winsberg on this stuff. And John Norton. There's like a collection of papers dealing with this problem about like the epistemology of simulation, how it relates to how we should think about experiments in particular. And so one of the questions in this literature is, well, don't we see a kind of intervention in simulation, or couldn't we think about simulation as performing interventions in some cases? And I think that's all well and good. I think what's really important is to keep track of what the target of the so intervention doesn't matter, I don't think. What matters is the causal connection to a target. Intervention is one way of getting causal connection to a target. Detection is another way. Observation is another way.
Maybe simulation is a way by itself.
Well, no, yeah. So I think we can say in simulation, one can intervene on a model, on a computational model, right? So you can, like I can give you a cool, let's see, I have this great instability and supernova picture that I want to show you. Where is it? There, this one. Yeah, I can, make a model of a supernova.
Yeah, but for example,
and intervene on that in my, in the process of simulating. But that doesn't get the right sort of connection to the world because the model is the target.
Yeah, but what if you have a model, or for example, you do a simulation of the large-scale structure, and then you compare whether the features kind of are the same. And in this comparison, how would you understand that between the simulation, which then again is perhaps also a model in the end?
I would want to say in that case that the computational side is providing, the bit of theory against which the empirical is going to be tested, right?
Okay, yeah.
Yeah.
But of course, so if I understand you correctly, it doesn't matter whether it's intervention or observation doesn't matter. It's whatever causal connection you want to create between the. Okay, thanks.
Mm-hmm.
Shall I now give it to Siska?
Yeah, please.
Thanks. Thank you. I have a sort of like related question. So I'm quite sympathetic to this, but I guess one way in which you could push back on the simulation point is that take climate simulations, right? They take as input some empirical data from the climate, right? Just from like measurements of temperature and stuff. And then they wind the clock forward, and then you get an output about what the global climate will look like. I mean, I'm simplifying hugely, obviously, but you see what I mean, right? And so I'm a little bit worried there that, like, if I just say my target is the climate without a time index, there's still a causal connection there from, you know, the original T0 when I got my data, and then I just put it into my computer simulation, and then, so would you consider that data empirical, or like, there's like a worry there about, like, is that data empirical? If you, in your view, if you want to avoid that data to be called empirical, you have to put in a time index on your target, but then are we defining our target in function of what our intuitions tell us? That is what is empirical data and what isn't? Or do you see where I'm sort of like stuck a little bit?
Yeah, I think so. I think that's a nice case too. And in general, I'm worried about like these things that look like kind of hybrid cases that have some empirical bits and some, you know, synthetic bits and some, yeah. But I think in that case, we could say, okay, so if we attend to what was the target, you know, that is causally connected to the production of the data that was then processed in this way to produce the result. That target is going to be, I think the timestamp is a good direction to go. That target, you know, will be different than the projected climate for which, you know, these simulation results are being used as the sort of theory side in order to, you know, be constrained by future empirical evidence. So I think, you know, we can have theory stuff that's empirically informed that can be constrained by other empirical results, you know. Yeah, so, but you want to say, like, is the target there the climate as a whole, just in general, rather than the timestamp? Yeah, I think this is, okay, so I think this is kind of similar to the National Ignition Facility cases. We can construe the target of the system in a couple different ways. We could construe the target very narrowly, or we could construe it as a token of this larger type of physical systems. So like, or in your case, like the climate now, or the climate like generally. And my feeling is that we probably, as long as we keep track of which target we're talking about, then we'll be fine. But I think the tricky problems and sort of knots in this literature around simulation and experiment come up when we equivocate on the target. Yeah. And presumably the questions that you can answer will depend, based on the empirical data, will depend on how you've defined your target. The target. Yeah, that's right. Yeah, so, right, I think picking out and defining the target happens from within the epistemic context, from, you know, using resources of the background theory that one's working within, and you might be able to take the same data, you know, and using the resources of your theory, construe different targets with respect to which that data has been produced. But that's gonna, you know, like, you'll be able to do different things with it, depending on how you construe that target. Yeah. And some things you won't be able to do. Yeah. Thanks.
This is just a short question. So this is for whole science. I have data, for instance. I have, you know, some data. I don't know where they come from. And then I have to construct this to say that these are empirical data. So astronomy or astrophysics is like, you know, matter physics or all of the branches of physics. So it's a way of putting everything together in the same line, in the same, you know what I mean, in the same quality of empirical evidence. No, so the whole physics is the same in this aspect. You know what I mean? It's just you can have this diffusion equation or diffusion data, and this diffusion data could be from a smoke or for a galaxy. So you have only empirical data when you have put everything in context.
Yeah.
You know that. So all of physics, for instance, is the same from this point of view.
I think this is a really general feature of, you know, empirical evidence, what distinguishes empirical evidence from what we, you know, from whatever we might want to do with synthetic or virtual results or theorizing. I mean, I think, yeah, this is a real general story. I think there are other really interesting questions that we could ask in the discussion about, you know, the sense in which astrophysics is distinctive from other fields of scientific research, and, you know, the connection to astronomy, the connection to cosmology. We saw a couple kind of Cosmo talks today, and I think that, you know, I think there are interesting reasons, you know, why astrophysics is distinctive as a field. Sybil Andrel, who I mentioned for Thesis 1, is a person who I think gives some good examples of how astrophysics is distinctive as a field. I think there are really interesting historical points to be made about, you know, the introduction of spectroscopy into astronomy and how that changed how that both changed the fields of research and the questions that were asked, but also contributed in new ways to really old mapping projects that have been going on in astronomy. So I think there's, you know, there's this issue of, like, you know, maybe astrophysics is more statistical than cosmology. Yeah, but that's debatable.
But this thing, you know, your theory is just everything is the same kind of science.
My
from
view,
this empirical point of view.
Okay, here's the view. You know, some people have argued that astrophysics is distinctive in the sense that, you know, it's really observational as opposed to being intervention. I think that, you know, not only is it not observational, right, that this is just the wrong distinction to hold on to. Instead, I think we should hold on to a distinction between the empirical and perhaps the synthetic, and the empirical and maybe other things too. But the contrast is really between, you know, the empirical and the non-empirical, and that contrast helps us in astrophysics, but is also a really general, you know, and useful contrast in all empirical science, and that sort of makes astrophysics on the same playing field in this sense. But, yeah.
Would we just say one little thing and link to the discussion? So right. A small suggestion that I have for how to treat the distinctions between Worley target and causal interactions in the National Livermore Laboratory example. So it strikes me that what you want to do there is to say the same properties are instantiated in the materials at the Livermore as instantiated in the supernova. So rather than thinking of the Worley targets as objects, may not make sense to think of them as properties. And then the idea that the properties are instantiated is actually very common across all kinds of empirical physics. I mean, sort of study systems over here and then extrapolate over systems that you suppose to instantiate the same properties. I mean, you don't have to go to astrophysics to see that kind of extrapolation of properties going on from within the laboratory to outside the laboratory. The so-called extrapolation problem is not a problem in astrophysics, it's a problem throughout empirical science. So if you think in terms of properties, then I think your problem gets subsumed under the general problem of the extrapolation problem. And then it doesn't look like it's distinctively an astrophysical problem.
Yeah, no,
so you go back to having, so that's another way of defending your view that it's pretty much really the same, and that astrophysical evidence is good evidence just like any other.
Yeah, I mean, I think that
evidence.
there is a kind of generic extrapolation going on there, or an analog problem going on there, or you know, some. I'm a little worried about the property. I mean, so we could talk about maybe the particular instability as a, I don't know if that's a property or behavior or how exactly we should talk about that. I was just calling it physics. but so I think I'm sympathetic to this idea that you can have that we can have something like this RT instability instantiated in the very same physics, identical physics. Oh, I'm worried, but maybe here's a direction to go. The identical physics instantiated in these different physical systems, the plastic and foam case, the supernova case, same physics. But I think you have to argue for that, as you're saying, as you do in any context, right. Biology, whatever. And that's what these researchers have tried to do by appealing to these similarity conditions, these criteria for similarity between the physical systems. What I wanted to say for this particular case was that I'm wondering if it actually doesn't go through in that particular case, given the nature of the experiment. But I think that's the kind of fine-grained microscopic level I want to do philosophy of science at, where we think about what are the exact conditions of this experiment, and are they fulfilling what the experimenters are saying they're doing? What's the kind of epistemology of this particular experiment? And I think you can see that sort of question very well in this case by setting aside the observation and intervention stuff and just kind of like focusing on that question comes to light when we look at what is producing the data, what is the target of research, how are the data related to the target, and this other stuff that's been talking about in the philosophy of science literature is not super helpful.
No, I agree with that. I'm just suggesting that that's going to go through more smoothly when you talk about properties.
With properties sound like spooky to me.
Supernovas, you cannot have them in this room. Mm-hmm, mm-hmm. But you can have some of the properties of supernovas instantiated in some materials, in some laboratory conditions, and then it doesn't look that different to what we do in most empirical science all over the place, and not even the natural sciences. I mean, the extrapolation problem is very,
yeah. I think I'm a philosopher enough to worry about that word property given its baggage, and so I'm not gonna bite too early on that one because
object gets even worse.
Yeah, sure.
So maybe this will kick off the discussion session, which is just as well.
Okay. Well, maybe just if I can just follow up on that point about the simulations for the instability. I think the way that I would see the simulations is mostly not in producing data, but in producing theory, if you like, or giving you the theory to confront the data with. And it seems to me that the value of something like this experiment would be not so much in trying to recreate exactly the conditions in the supernova, which are impossible, but in validating the approach of simulating the theory. So you have the theory being the microscopic physics, which then goes into the simulation codes. And then if you can reproduce what happens in the lab with certain parameters of conduction and so on, if that works, then that would give you confidence that when you then ran your simulations with the supernova conditions, the supernova parameters, that it would give you confidence that the theoretical side of things was robust.
I'm not sure. So, I think we could simulate this sort of instability, or we could try and produce it at NIF. Why trust the NIF results in the laboratory more than the simulation? I mean, a detractor might say, well, you have to do all this work, even for the NIF system, to argue that it has anything to do with supernovae.
Yeah, but I think the interesting comparison would be between what comes out of NIF and what comes out of a simulation where the conditions have been set to reproduce NIF. Mm-hmm. And if that works, then you can change the setting to supernova conditions,
right?
Make some predictions and be confident that those can then be confronted with the supernova data.
Yeah, and I think that's what folks are doing, but I still have this worry that I think Mauricio is pointing to, which is that there's still some extra argument that has to be made that once we make this extrapolation to the this other scale, that things aren't going to go wrong. And
they might.
And I'm saying you might very well be able to make that argument. I think there are some cases in which you can make that argument. It's just that the argument needs to be made. Yeah.
Agreed. Yeah.
But I'm just wondering about this NIF, experiment in particular. I'm wondering if it's self-undermining given the nature of the experiment. I'm just really curious to think more about that case and see what's going on there. But because one of the criteria that they need in order to make the similarity argument is the very thing that they seem to be investigating.
Yes, I think I'm questioning whether it needs to be self-similar.
Well, I think So why not?
Well, I think if you've shown that the simulations can reproduce an experiment in some range of parameter space and it works there, then okay, it might go wrong somewhere else, but at least it gives you confidence that if it can't reproduce that, then you know that it's not.
Right, I agree with you there, but I think the getting to another scale, another context requires argument because you can, we know all kinds of physics that works at some scale but not at others, and locally here but not over there, and so I think you have to make the argument.
Yeah, fair enough.
When you do a simulation, you can find results and find out these results in the world. So you put the simulation, you put your equations, and then you have, for instance, a collapse with two galaxies. And you haven't seen this kind of, of galaxies. And then you put your telescopes and you find these galaxies. Now simulation is just putting evidence that someone could be there. It's in new experimental data. So you think that your theory is really good, and the results that are in your theory could be in the world. Then the thing has changed completely the view. It's not you are not using the simulations to find your results that you know perfectly. You use the simulations to see if the world has this kind of object that you never have seen. So you can use the simulation to find out things in the world that you never saw.
Right, so it has predictive power.
Yeah.
Right.
Yeah. And you find that.
Do you call it data? I wouldn't call it data.
Data that you have, when you put your simulation, then you have new data, and for instance, it's very visual. Then you have a collapse of two galaxies, and then you can put your telescope and you find these kind of objects, and then you have a kind of experimental data from your simulation. I know this is interpretation, but it's you're not just confirming or validating your theory. Your theory is using in the simulation to find out new kind of objects that you never knew. That's the point. So it's the point of view.
Right. Okay. So thank you very much, Nora. And thank you.